what yours looks like right now?
Approximately, yeah. Yeah.
Okay, so over in files, these are all the files that are required to run whatever the project that we're running. And so we'll click on .r, this lesson 3.r, and that will launch the script up here, and your console should be blank or something like that here.
Okay, got it.
Is that adding up?
Yeah, thank you.
Okay, cool. So so the first thing we're gonna do, and many of you, I've already run through this on my RStudio Cloud, so it's not showing up for me, but once you launch this, there should be a little yellow note that comes up here, like it looks like there's TinyVerse, would you like to install it? So you can go ahead and click install. When you want to install a package, normally it's usually like this. So I'll go ahead and execute that.
What if you don't have that little yellow thing?
Then go ahead and do this install packages with TinyVerse in quotes.
Unless you're already TinyVerse, in which case you're good to go.
Yeah, so I already have it, and so I just installed it again. So now I'm just, yeah.
And RStudio Cloud may come with it.
No, you have to do this.
No, just kidding.
Yeah, so go ahead and let's make sure everyone's up to page, because this will take maybe up to like 2 or 3 minutes for each person. So I want to make sure everyone's on the same page and doing that. So please chime in right now, and we can work on troubleshooting that if people have questions. So I'm gonna keep talking, and maybe Jacob and Ella, and if there's other instructors online, I can't see everybody here. If you guys want to just watch the chat window to see if there's like any issues that come up. But once install packages is right, so these are packages. R comes with R has like a lot of base R functions. That's kind of what we mean by base R versus something else. So we'll be using those terms today. And so when we talk about things in the TinyVerse or dplyr or plyr or ggplot, all those are packages that are kind of belong in this umbrella of TinyVerse. And so when we are installing TinyVerse and we actually load TinyVerse, which I'll execute the library loading, then we're actually installing several packages. I think that your install is probably still, I know when I did this initially, it took several minutes. So hopefully that's all working for everybody. So I'm going to keep talking about TinyVerse. So the past two lessons, we've talked a lot about different functions in base R, and there's so many things you can do in base R. A lot of us, at least myself, and maybe Jacob and Ella can comment, use a lot of the things in TinyVerse because it's just a little bit more, it's more versatile to go between different packages. And there's a plotting package, ggplot, within here that also lets you kind of put all of your code and makes it really intuitive, I think, and kind of pretty, and then gets to the plotting stage, which is usually a major goal. So I'm gonna go over some base R functions today, repeating those functions in using a TinyVerse package or in the TinyVerse way. And that's kind of going to be the extent of the lesson. I also took a lot of the questions and things that people put in the Slack channel that they were interested in learning how to do to data frames. And I think I addressed most of them here. We're going to continue this theme, I think, next week as well. So we'll continue adding questions if you want, and we'll continue just going over anything and everything that you can do with data frames. I think I talked to Ella about this, and I asked her how she feels about TinyVerse, and she said that it makes her life easier and makes everything easier for her. So, and I agree with that. And there's also so many different ways to do things in R overall, and there's a lot of different functions in TinyVerse. I'm not going to cover all of them at all. So Jacob and Ella, please chime in, but also note that we'll have other lessons that will cover different components of it, and I'll mention some of those along the way. So I'm going to do a quick pause here and just make sure I think everyone is doing okay. So there's something about smoke coming out of a laptop. Okay. All right. So I'm going to ignore that for now. So yes, every time you load right? So usually, actually, what my code usually looks like is the first few lines are usually the installing of different libraries, and because you need to load that each time. So today we're going to be using some test data, and I'm going to upload it here using this, and I'm going to view it briefly just to show you what it looks like. Lists, the first column is listing taxonomic identifiers that have a semicolon and some other characters separating the different levels of taxonomic assignment. MAG identifying numbers. MAG stands for metagenome assembled genome. And then we have 4 genes that have kind of been randomly chosen and has the gene counts underneath them.
Sarah,
And,
I'm sorry.
yeah.
There's been a request that you put this on full screen just so that people could see it better.
Yeah.
And maybe if you can increase, great, awesome.
Is that better?
Yes.
Okay, thank you. I wish I could make this even larger. All right. So that's like what the format of the data frame is that we're looking at today. There was one request to just quickly review data frames versus matrices. So matrices again have a single data type, right? So if I look at the class of data, I've imported a data frame, right? This is what it looks like when I use the head function, and then looking at the structure using this function str, I see that my data is made up of factors and integers. And so if it was a matrix, it would all be one data type, whereas this data frame has 2 different data types. And here's our first TinyVerse way, where instead of my previous function that was read.dlim, this is a read_dlim, and I'm going to import the same data, but now it's actually in something that's called a tibble. So we'll again look at the class of that and look at the structure. And so this is showing it's a tibble, and again, it has the same overall format. And tibble's kind of a very specific type of data frame, but in TinyVerse. I generally, because I use a fair amount of base R and TinyVerse functions in the same code, I generally default to using just data frames. And I'm going to talk primarily about data frames today. I'm going to give Ella and Jacob a quick minute or quick second if they want to chime in about their extent of using tibbles, and maybe future lessons if they think that if maybe next time they want to tackle that or during office hours or something. Jacob, Ella, any comments about tibbles?
Tibbles are a kind of data frame. They're very similar to data frames. They behave in almost exactly the same way. TinyVerse likes to coerce your data frames into tibbles a lot, so sometimes things just become tibbles without you even expecting it. The big differences between tibbles and data frames are that one, tibbles default. Well, actually, the way that they put it is that they complain more and they do less. So one of the things that they don't do is they tend to not have row names associated with them. So you just have a column that you'd use instead of row names. And they often default to storing text variables as strings of characters as opposed to factors, which are a little bit easier to do, as characters are a little bit easier for new people to deal with. But for the most part, you can usually ignore the difference between the two, and things usually just
and I'm gonna show you later on how I personally write my TinyVerse syntax related code, because and always kind of default to data frames, because as Jacob said, they often just end up as tibbles randomly. And just to backtrack, I mentioned the differences between matrices. If I use this function to actually convert my data frame into a matrix and then look at the structure, now everything's defaulted to character. And so that's an example of, right, I had this data frame that was 2 different data types, and in the process of converting it to a matrix, it converted everything to one data type, because it's a mix of things, our defaults to character. Okay, so I'm going to continue on and start looking at some base R functions and then go into the same functions, but how they work in dplyr. So the first one is looking at the call names. And looking at the call names from this data that we're looking at today, right? I have taxa, the MAG identifier, and I have these 4 genes. And there's 2 things that I want to do to these gene column names. First, this is bothering me because it appears to be some kind of typo where gene is not capitalized, all letters are not capitalized, and D is not capitalized. And if you wanted to export this table for like a supplementary figure or supplementary table for a paper or share it with a collaborator, it might be nice to have gene A, B, C, and D in some kind in the alphabetical order. So I'm going to show a couple ways to modify this table. And a lot of this was covered previously, but I'm just reviewing it because we'll repeat the same functions, but in TinyVerse next. So in this command, we're using call names again, but on the outside in square brackets, I'm listing 6. And this is indicating that I want to modify the 6th column. So 1, 2, 3, 4, 5, 6, that's gene D. And this is going to be the new name for gene D. And then if I look at call names, gene data now gene D is all capitalized. And if I want to change the column headers for more than one column, this would be the notation, right? Where I've isolated those columns in the square brackets, and then now I'm listing several of the column names. If this had, for instance, let's just try to break it. If I'm listing 3 through 6, but only listing 3 items, then R will actually give me an error. So, right, because I only have 3 items listed when R is looking for 4 names to replace those column names. So again, my output looks good here, and I have that listed twice for some reason. And now I want to look at how to reorder this. So I have 2 ways I'm reordering this data. In the first one, I have gene data, and then in square brackets, I'm selecting my column names, but in the order that I want them in. Recall the comma indicating rows and columns within a square bracket. In this case, because everything's falling after the comma, we're isolating the column names. And here I'm listing every single column name, but they're in the order that I want: A, B, C, and D. Oops, I think I did something wrong here. Did I list? Oh yeah, I renamed this because I poorly renamed this here. So I'm going to go ahead and fix this by going 1, 2, 3, 4, 5, 6. And this needs to be gene A. So let's check that again. And so I have my column names in the same order. Now I've actually listed them in I just messed this up, I'm sorry, hold on. So the great thing about R is that you can always go back and restart your code. So now I've restarted, sorry about that. All right, so now I have gene data. I'm gonna use this. And my column names again are in the order that we don't want, A, C, B, and D. And so to reorder them, I'm selecting those columns in the order that I want. And then now they're listed A, B, C, and D. Another option to do that, right, is to actually use the numbers of the columns. And so here's gene data, and then in the square brackets again, I'm selecting those columns based on the numbers. And so recall, I'm gonna just go over the notation for this. I'm pretty sure Ella did this last time too, where I want to first select 1 through 3, 1, 2, and 3. And then I want to select column 5, which is here, and then column 4, and then 6. And so that's why the order of these numbers comes into play here. Is everyone, I messed up my, the order of how some of these were running. Is everyone caught up though? I just want to check in. Okay. So both of these get me the same thing where they replace the columns, but I want to make a note that one of them is more reproducible than the other, which is on line 57, and that's because I'm actually naming those columns. So if I produce another data frame that has the same genes, but different taxa for some reason, or a different set of mags that I want to compare, and I want to reuse this code, then it's more reproducible, and we'll be able to I'll be able to put in any data that's in this general format because I'm actually selecting it by the column headers. So as long as those column headers remain in another data table, it still works. But in this case, with these numbers, you know, what is column 6 in this data frame might not be column 6 in another data frame. And so that presents a possibility for an error to come up. Okay, so now we're gonna do an introduction to TinyVerse using and looking at the renaming and reordering functions. So I'm going to start again, re-importing this data. And then I have my original data frame here, taxon, mag, and then the genes listed. Again, I have that original typo and the order that is less desirable. And I'm going to first use this function called rename. We'll pull up the help menu for that. Remember, that comes up over here if you need to reference it. And we'll explain this notation or this syntax that's kind of unifies the TinyVerse language or something, where we have the original data frame that I want to modify, and then the command of what you want to do. And in this case, we want to create a new column. We're using rename to create a new column that's going to be gene D in all capitals. And that new column is going to be equal to gene underscore D, the not capitalized one. And that's how we'll rename that column. And this is what's called a pipe. And so it links each of these commands. And I'll talk about, I'll go over that more in a second. So executing this command, now we have gene underscore data fixed because I'm setting all of this equal to a new R object. And we'll check that actually by going over here and hitting view this time. And now I've corrected for this gene D typo. The next command has a similar syntax, right? I have now, instead of using my original data frame, I'm using gene data fix, the pipe, and then I'm using a new command select. And this one, similar to the previous approach where I'm listing those columns, so I'm selecting those columns, and in this case, I'm selecting the columns in the order that I want. And again, here we'll use view again. I'm changing this to A, B, C, and D. Now, this is one command that I just learned in the process of writing this. Jacob introduced me to this, where writing all of these can be a little bit cumbersome. And so one way to, and maybe you have, many more columns in this, and one way to avoid typing too much, I guess, is to use this term here, it's everything. And so comparing these two lines, this is selecting these columns, taxon, mag, gene A and B, and then just put everything else back the way it was from my original data frame. And so this will give me the exact same thing here. And then maybe we can help menu really quickly. Looks like that is across many TinyVerse packages. Okay, and so now I want to talk about the importance of that pipe operator. And this is kind of where we start learning what the syntax of TinyVerse is, where in this case, we're doing the same thing where we have a new data frame or a new R object that we're going to set everything equal to. And on the other side of that is my original data frame. I have that pipe operator. On a new line, I'm using the rename command with another pipe operator, and then the select. And so now I'm able to put all these into one. And then instead of doing that in two lines with an R object, setting a temporary R object up, I'm able to execute this in one go. So I think the rest of the lesson is going to kind of go the same way, where I'm going to show a couple of different TinyVerse specific operations, and then how we work to compile them. And once getting the syntax down, I think is at first kind of confusing, but once you figure it out, it's actually really fun to play around with. And I think it really does make my code look a lot tidier, to put it one way. Okay.
Sarah, there is a question.
Yeah.
What is the best way to rename all the columns using TinyVerse?
All the columns using TinyVerse. That's a very good question. I would say I would only know how to do it the same way that I have up here. So, right, if we wanted to modify this, all right, so I'm going to show this first. But gene D is, I'm going to set that equal to gene D here. And then I think if I kept going, if I wanted to do gene CA for some reason, wait, right? I think I would have to type each column header or in the same way. So I'd have to type this over my 6 column heads. Does that make sense? So I'd have to just type that 6 times for whatever you want your new header to be. Does anyone, Jacob or Ella, does anyone else have another solution that would be quicker? But I think that's the only one.
Googling it right now.
There's also one other thing. I can actually go up here and modify this earlier command to address this question, where we use this. I'm going to write some new code, so I might change my line numbers here, and I'm going to set this equal to temp to modify it. So I'm going to modify temp. So if I want my column names to do it this way, and I'm sure there's a way to do this in TinyVerse, but you can do new names and then equal that to this. And then this would be new names here. And so I think that this is the other way. This is actually more typing than what I previously had, but often this is what I end up doing because this list of names I use several times. So later on, when I want to reorder something for a plot or another input for data, I can recall new names several times throughout my code. And so that would be one way to streamline that. And then I think that you can also introduce new names from here into the TinyVerse code here as well. Does that make sense? Jacob and Ella, maybe? I don't know.
Yeah, there are functions in TinyVerse for doing sort of regular expression renaming of stuff. So, for instance, you could rename all the things that are in lowercase into uppercase.
Okay.
But if you just have some vector of like these are the names that I want to have, and but those are different from the names that actually got loaded. Usually, I would just do what Sarah is suggesting, is just say the column names of gene data are actually now this thing, and save it the way you do it in base R.
Cool. All right, we should have a regular expression day. I think that'd be fun.
Can I add one more thing?
Yeah.
So the pipe operator, what that does is all it does is it takes the data to the left of the pipe and it sticks it as the first element of the thing to the right of the pipe. So all the functions in TinyVerse, I'll expect a data frame or a tibble as their first element. So select takes as its first thing as a table, and then it takes the columns that it's selecting. So what the pipe does is it says you can put the thing on the left and then pass it to as the first argument to the thing on the right. And so you could do all these same sort of things with lots and lots of nested parentheses, and that's how people would do stuff in base R. Or you can do it one line at a time and keep saving over another variable. But the pipe allows you to essentially many nested parentheses things, so that instead you're sort of looking at them as this first element passes it to the next thing, which passes it to the next thing, and so forth. That's all.
Thanks. Okay, so I'm going to go into subsetting some data. And this was another question that I got in the Slack channel. We're going to continue using this this data frame that ends in fixed up that we last used with the first TinyVerse function. And this is using commands in base R, and this is using subset. And so what this function is saying is that I want to subset this data frame, and I want to select it so what I have highlighted here is indicating that in the column gene A, it has to be equal to 0. But then this exclamation point on the outside of the parentheses makes it the inverse. And so what I'm selecting is that I want to subset this data frame so that gene A does not equal 0. And so I've written, this is actually 2 ways to do the exact same thing, right? Because if gene A does not equal 0, then it is above 0, because these are all gene counts, so there's no negative values. And so these are both doing the exact same thing to create temp1, which now all of gene A IDs, I'll go ahead and go into view here. I've subsetted it so the data only has gene A that is non-zero number. So again, this is in base R. I think I have several other, there's similar examples of how to kind of add on to this. Like for instance, if you only want to subset things that have gene A is greater than 0 and gene D is equal to 0, for instance, right? If you're looking at a full pathway and you want to make a comment on what mags or rows in this case have gene A but don't have gene D, for instance, then that's one way you can work to address that question. So let's repeat the subsetting function with TinyVerse, which is using the filter command. I'll go ahead and pull up the help menu here. Right, returning rows with some kind of matching condition. And it's really similar, right? I have this gene A greater than 0 and my original data frame here. And again, this is the exact same thing, same kind of notation, but now I'm using a pipe operator, where the filter function now includes only the things that are conditional. In this case, I'm selecting things that are greater than 0 for gene C and gene D. And then I'm going to get temp tidy. This is showcasing the same thing, but in different forms, where here my conditional arguments are within the same parentheses separated by an and, so it's indicating that both of them will be done. In the filter command, you can also separate these with a comma. This will get you the exact same thing. And then a fourth way, which is more typing, where you add another pipe operator and then you do filter again. First selecting for things that are greater than 0 in C and then greater than 0 in D. And then here's another approach, again, using the exclamation point, where I want to select things in my data frame, select rows in my data frame where gene A does not equal 0. And so this is one way to do it, where you put an exclamation point and a equal sign. Another way is to, again, use that where the entire condition is in parentheses and preceded with an exclamation point. So we'll go ahead and look at temp2 tidy again. And again, this is when gene A, they're all non-zero values. So this was all filtering or selecting rows based on a condition from using numerics, right? It was looking at things that were greater than 0, but you can also select things based on name. And so this is kind of similar to what I showed, what I did earlier to answer that question about column names, where I'm setting a series of names equal to an R object. Right, the C stands for concatenate, and where in parentheses I have different mag identifiers. And so if I wanted to look for only these 4 mags, then I can list them in this function, and then I have mags I want. Oops. And lists all the mags I just set this equal to. And then inside the filter command, instead of using the numerics, I can look for that column, right? Just a reminder what the column names are for gene data fixed up. Mag identifies those mags, and I can use from the mag column, I'm going to select mags I want. And this it's kind of similar to the pipe operator, where it's connecting two things, and it stands for matching. So anything in mag that matches the names listed in mags I want, this is how I would use this. Note that, and this is what that's indicating and using that matching notation here. Note that up here, when I was using these values, right, this is using the equal sign, greater than or less than, and exclamation points. But down here, when we start getting into naming factors and matching factors, this is, you have to change this to the percentage in and percentage sign. And so now I'm going to do the same thing where I actually combine all these statements together, right? So I have Gene, right? So I have filter and mags I want. And in this case, I'm actually filtering by both the numeric and selecting the mags that I want. So then I have Gene data filtered. And this actually selected out of the 4 mags that I wanted, which were chosen at random, only 2 of them had non-zero Gene A counts. And so it subsetted only 2 rows from my data frame. Does that make sense of how I use the filter command? I want to check in and see if there's any questions I can address now before we keep going. Okay.
Yeah, Sarah, there's a question on what if the mags I want are in a separate table? Is it possible to filter one table column using a column from another table or list?
Yes, that is a very good question. There are 2 ways to approach this. One of them I'm going to mark for a future lesson or office hours. Make a note, Jacob and Ella, maybe someone can go over merging tables, because there's a lot of creative ways to merge tables, and that could be one application to address this question.
Actually, did that in previous class.
Okay, yeah. I'm sorry. I don't think you used the dplyr ones, right?
Oh, no, just the base R merge.
Okay, yeah. Some of the dplyr ones allow you to do like anti-join and stuff, and I don't remember if base R does. So let's review what mags I want is, and I'll show you how to pull that out of a separate table using the same data table that I have here. So mags I want, look at the class here. This is a character because it's listing all these names together. Now, so if I look at my original data frame here, I'll just print the first 2 lines. And say you have, imagine this is a separate table, and I want to find all the mags from this table and subset them from another table. So all I would need to do is figure out a way to isolate that column of those mags that I want and bring them into this form where the class is a character, and then I can use them the same way I'm using the other ones. So the way I would do that is, let's see, mags from table as character, because I want to set it equal to a character. And then I would do Gene data, isolating a column. In this case, I would isolate mags. Okay. And then from this, mags from table is again a character. Previously, the mags I want is only listing 4 things. And so I can actually look at the length of mags I want, and then also print out length of mags from table. And the original mags I want were only 4 items, but now what I've subsetted in this new character is 84 different mags, because that's the length of my full table. So that's how I would do that. One other quick thing that I'll just throw in here right now that is in base R, and I believe Ella also covered this, was if these mags were not unique, for instance, they're listed several times for some reason, then you can also include unique here, and it would only pull, like if there was mag 3 was listed several times, in this final character, mags from table would only list that mag 3 once. Does that answer your question?
Yes, thank you.
Cool. Okay, so we're gonna start again and actually string everything together and just show you the simplicity of like the overall TinyVerse syntax. Again, I'm starting with my original gene data, incorporating the rename and selecting, reordering the columns, and then again, doing that filtering. And then this is not named. Yeah. Okay, so this is an example of how I strung all those together. Okay, so now I'm going to go over the last part of this lesson, which is converting things into long format. And this is, I consider wide versus long format. I consider the long format of data to be more versatile in R, especially when we get into plotting, which we'll do soon. So I wanted to first compare long and wide format. Jacob and Ella, do you guys have comments on long versus wide formatted data?
You need both of them for different stuff, and so it's really useful to be able to go back and forth between long and wide.
Yeah. I think it took me a while though to get used to how to do this. So I think just getting in and playing around with some data and converting it back and forth is helpful. Yeah. So the commands, they're commented out here, but the pivot longer and wider functions are here. I'm gonna go over my original data frame, right, listed here. This is in wide format, where I have several attributes and then all of my gene IDs here. We'll probably use some kind of OTU table or ASV table in the future. And typically an OTU or ASV table, Ella had one last week that was in wide format again. It had the OTU IDs on as a one column. So each row was an OTU, and then samples were columns going across. And so that's in wide format. So to show you what I mean by long format data, we'll use this pivot longer command, which I'll go over in a second. Now, instead of having several columns that are my numbers or the actual values that I'm looking to investigate, I now have taxa, mag, and then I have this one column called gene, which lists the different genes, and then I only have one column listing the values. So this is the long format version of my data frame. And the way I did this was using the pivot longer command, which I have the help menu here. The first thing you do is isolate which columns that you actually want to basically smush in. And in this case, I selected gene A through gene D, and I wanted those to go into a new column, and the head, or the name of that column is head. And then all the values that were associated or underneath these previous wide format columns are now put into a new column that's called count. And so that's how I did this here. And the reason I consider long format to be very versatile and in R is because of what you can do next with this. And probably my opinion is very heavily influenced by TinyVerse usage. So before doing that, I want to introduce one more command, which is actually splitting splitting columns. Note that in this long format data, I have this one column with all of my taxonomic information, and it's separated by a semicolon and some extra characters here. And you often want to know the phylum, class, or order level. And so you probably want to split that into separate columns so you can start ordering things by family or subset different families and look at the data. And so I'm using this command called separate. And I'll execute it first to kind of show you what it looks like. The output is a tibble, and it has the original column here with everything in one, and then it separated that out where the semicolon is by phylum, class, order, and family. And that's designated here where I'm separating the column taxon. The new headers are listed here, and you do have to think about how many you think you'll get out. So it's probably a good idea to like look at your data and see how many semicolons and how many new columns you have to name. And then sep here stands for separator. And in this case, I put in semicolon and the remove equals false because I wanted to keep taxon. So as a test, I'll change this to remove equals true. And now my new data frame has, doesn't include taxon, and it includes all of my new columns that I created from here. So let's string that all together again, where I have my fixed up data, I'm pivoting it longer, making it a long form data frame, and then I'm separating that one column again. And I've added one more thing that goes back to what Jacob said previously about tibbles, where TinyVerse likes to provide you your final product, which I'm setting everything equal to, as a tibble. And so at the end of my at the end of a lot of my commands, I end up putting an additional pipe operator and data.frame to convert the final product back into a data frame, which is what I'm showing here. We're starting to, I don't want to go too long, so I think I'm going to go over this next example on how to calculate a mean from a long format data, but we'll plan on going over the rest of this, or you can explore the rest of this at office hours, or we'll kind of continue this because there's a lot more to uncover in TinyVerse. So here's my gene data long format, where I have everything separated into different taxa by column, and I have, again, one column that kind of has my variables. In this case, those are genes. It's the different genes that this table lists, and then a single column that lists the values. And so I want to average the values that I see for each gene at the family level. So, at the class level in this case. So looking at my data frame really quickly, I have this cyanobacteria at the class level, and I want to know what the average gene count is across all the cyanobacteria. And so to do this, I'm going to use this group by function. And what group by does, and I like to think about it as my final table, these are my two columns that are going to be in place. These are my two final columns that are going to be unique in my final table. And in my final table, I want to know the average for each gene, and I want to know the average for at the class level for the taxa assigned. And so this is me subsetting those columns from gene data long, and my new table will have those as like the main unique columns. And then I'm using another pipe operator and going over summarize, or using summarize command. And summarize works to create a new table, and it's a new summary of your data. What's happening here is that I'm making a new column called mean, and that column mean is going to equal the mean of count. And TinyVerse, or in this case, I believe it's dplyr, knows that it's averaging the counts when gene and class are unique. So it's only going to average things in gene A only for cyanobacteria. So we'll take a look at that. And just to give you an idea, I'm going to look at the dimensions of my data using this function. So originally I had data long. I'm going to use a semicolon to print out two different things. And then my new data frame is mean underscore class. And the dimensions, my original data frame was over 300 lines long because everything was in long format. My new data frame is only 56 lines long, which means that that it kind of summarized the data down. So to look at it, now I have the class level listed, I have the gene, and then I have the mean within that. Let's see. Yeah, and then another way, yeah, actually, that's all I don't want to go over, so that's all I'm going to go over right now. But there's other ways to start adding on to the summarize command, right? Because we can start doing the standard deviation of the count. So we want to do standard deviation equals SD count. And I think towards the end of this code, I actually list some other things you can put in here. We can start getting fancier with like putting in other, what am I trying to say, equations into this summarized separated by a column, and it'll start adding new columns to my data. So here I'm calculating the mean and the standard deviation of those genes at the class level. So this is the main way that I work to summarize my data frames.